Good evening, everyone. Welcome to the McDonald Observatory live stream. Really glad you can join us today. My name is Saul Rivera. I'm one of the public program specialists here at the McDonald Observatory Visitor Center. And today I'm joined by Dr. Teznie Pugh, our superintendent here at the observatory. And Teznie, tell us a bit about yourself.
Thanks, So yeah, I'm the superintendent. That means my job is to make sure the telescopes keep operating and that the staff are happy. But I do have a background in stellar evolutionary research. My research right now is mostly looking at finding planets around other stars. But I started my life researching red supergiants and understanding their evolutionary trends.
Awesome. Thank you so much. And we're going to get to learn a lot more about that. I'm also going to get to learn about that, which makes me really excited. But for those of you just joining in, welcome to this live stream. If this is your first time joining, welcome. Hope you enjoy. The way the stream kind of works out is throughout the stream, we do have a live chat feature. If you have any questions or just want to make a cool comment about what we're looking at or anything of that sort, just feel free to type into the chat. We do have a moderator on standby that will be responding to the questions. And if there's any question that seemed really cool, they will pass along to us to answer. Also, the stream will be recorded and will stay up on our YouTube channel, just McDonald Observatory on YouTube. So if you by chance need to leave early or aren't able to stay fully, feel free to join in on that side. And kind of a bit about where we are. Even with the McDonald Observatory is a research branch of the University of Texas at Austin, but we live very far away from Austin. We're out in West Texas. This is a picture taken by one of our colleagues, Stephen Hummel, of the nice dark sky here because you want to be somewhere out nice and dark for research astronomy. Where I am currently at is down at the Visitor Center. So we have a telescope park and amphitheater. I'm inside one of the domes, the telescope of the 16-inch in diameter. So here's a kind of a picture of how it looks like from the inside. I'm in the building. You can maybe kind of see it behind me. It's kind of weird. And also, if you that's also why I look really different. The camera is not black and white. I have a infrared camera, so I don't know if infrared's the right word, but I have a camera that helps us see better in the dark. So my eyes are really weird because I'm not possessed, even though it's this spooky season. But it's just the lighting. Actually, the shirt I'm wearing is a black shirt to give you an idea of how this lighting kind of works. And tonight we're going to be talking about binary cell evolution and also Novae and also the TCRB Nova that's going to be occurring soon. Hopefully, we're all kind of waiting for that to happen. Uh, and also have some cool live views to go along with it. And to kind of talk about the subject of Teznie, tell us a bit about binary stellar evolution.
Thanks, Sol. Yeah, so I shall talk us through some binary star evolution. So I'll start with a brief introduction to different types of binary systems. Then I'll do a refresher of single star stellar evolution before moving into how binarity and the interactions between two stars impacts their evolutionary pathways and how we end up with something like the Blaze star or T Corona, where we're going to see this intensive brightening, hopefully within the next few months. And finally, I'll end on some of the science of planetary nebulae and how they get their shapes and interesting features. So I've actually asked Saul to look at Albireo to start with, and you'll notice on my slide I've put detached binaries. So detached binaries are stars that do not interact with each other, so they both evolve in their own single star format. And I've put Albireo question mark because Albireo, while it is a binary star to look at, it might just be a visual double, that we just see it as a double star because the stars are close as we observe them, but may not actually be dynamically paired with one another. We don't actually know. And if they are, the orbital period is enormous, 100,000 years or more. For this system, but it's a great one to look at because it's a really pretty binary star and it's great to get early in the night. So if it was a binary system with an orbital period that long, the stars would be so far away from each other that even as one of the stars evolves and grows in size and radius, they wouldn't be able to interact with each other. So if I look at this slide, what I'm showing here are the stars. So I've got a blue star and a yellow star, and the weird teardrop-shaped objects around them are what we call a Roche lobe. And this is a scientific description that says once the material of the star goes beyond that point, it is close enough to the partner star that mass will begin to transfer from one star to another. And that is why the binary stars impact each other as they evolve. So the second middle image shows what we call a semi-detached binary. And this is where one of the stars will evolve earlier. It will fill its Roche lobe as it grows in size, and we'll talk about that on the next slide. And as it fills its Roche lobe, it will begin to transfer mass onto the partner star. So we'll think the classical example of this is the Algol system. And this is really obvious in that system. For those of you that have looked at it, it is also the current status of T Corona Borealis, the Blaze star. So we'll talk a lot about this type of system as we move through the presentation this evening. And then the final type of binary, what we call contact binaries. And these are really interesting. This is where both stars fill their Roche lobes, and it could even be before they begin evolution, that they could be so close together that they are already sharing mass with one another before they start their evolutionary process. So that's called a common envelope, and it means they literally are sharing matter with each other. So the gases move between both stars.
Oh, that's so cool. And actually, kind of before we continue, might as well show the example of the detached binary, so Albireo. And if you're wondering how close they look to each other, like in the night sky, this is how close they look to each other. You can see they're basically neighbors. Actually, Albireo is actually visible to the naked eye, actually really clearly, is in the constellation of Cygnus the Swan. Basically, where the head of the swan would be is where the stars are. Basically giving the stars, the swan, heterochromia, so two different colored eyes. And you notice one is brighter than the other. The brightest one, Albireo A, is about an estimate about 328 light years away from us. And for reference, a light year is about 6 trillion miles. Well, and it's about 1,000 times brighter than the sun. While Albireo B, the smaller one, is a bluish color, and it's only about 200 times brighter than the sun. But it's still very bright. As kind of Teznie mentioned, if these were a binary system, the orbit will be extremely long because actually they're almost 60 light years apart in distance, which basically you could say is about 360 trillion miles apart from each other. So it's going to take a good while. And another cool thing about this, so we're using a black and white camera to see details more easily, but when seeing through a telescope, even like a smaller telescope, one that people might have in their backyard, you can actually notice that they are different colors. So here's an image taken by Richard Yendrick of Albireo, and you can see the color difference. You see there's one yellowish golden star, Albireo A, and one bluish one, Albireo B. You can actually tell you can tell the color difference apart, which gives us an idea of the star's temperature and can also give us a glimpse into their life, where they are in their lifespan. And speaking of the lifespan, now let's pass it off back to you, Teznie.
Thank you. So as I said, the next thing I wanted to talk about was stellar evolution in general, because that will move us into how we get to a system like T Corona. So all stars start life as a cloud of dust and gas somewhere in the universe that is massive enough that it can self-gravitate and condense. And the mass of that cloud will impact the type of star that is created from that collapsing gas cloud. And that will tell us whether we get a blue supergiant, a star somewhat like the sun, or if we get a very, very low mass, very red star that we would call an M dwarf. So you'll see this on this nice image here taken from Chandra's X-ray Observatory's website. So the high mass stars, I'm not going to talk a lot about, although they are quite impressive as they evolve. They'll fuse their hydrogen in their cores very, very quickly and result in supernovae, neutron stars or black holes at the end of their lifetime. What I wanted to focus on actually is our intermediate mass stars. So these are stars between a solar mass and 5 solar masses, at their creation. And as they evolve and stop fusing hydrogen in their core and move on to fusing other elements, their outer shells expand and cool. And this is to do with the conservation of energy within the star. And as they expand, they become what we call red giants. They go through their red giant phase, and eventually the core becomes completely inert. There is no fusion taking place of any elements, and slowly the outer layers of the star expand, just leaving a bare core white dwarf. And that's what would happen for a star like the Sun, for example, because we don't have another star in our system. When the Sun dies, eventually what will be left behind is a white dwarf, a carbon nitrogen or helium white dwarf at the center, with a cloud of material from that star that has expanded outwards over tens of thousands of years. And that's what we traditionally thought was the cause of planetary nebulae, as we went through them. But we'll talk more about planetary nebulae at the end. I just really wanted to focus on this progression from protoplanetary cloud through to solar-ish mass star, through to red giant, through to planetary nebula. Because what I'm going to do is I'm going to focus on how this changes when you put a second star in the system and all of the mass gets moved around. Because as the star expands in our solar system, the Sun's surface will just absorb the inner planets. They'll get eaten up and made part of the star's gaseous outer layers. But in a system where there's another star, the star has so much gravitational force of its own that it starts to take the material onto itself, and it really impacts the future of the system.
Yeah, and kind of on the note of like where the stars themselves are actually born, we actually do have a stellar bird. Getting along a little bit of tongue tied. We're seeing an area where these stars are actually being born, which is here. So you can see this is known as Mezzi 17, the Swan Nebula. So this a star-forming nebula that's called the Swan Nebula because it does kind of look like a swan. Some people sometimes have a hard time seeing the swan, so you may know it by its other names, which include the Checkmark Nebula, the Omega Nebula, the Horseshoe Nebula, or the one that I see most easily is the Lobster Nebula. So for me, right now, it looks like a lobster kind of swimming upwards, and it's missing its left claw. And astronomers are sometimes very literal with the naming of things. People ask, why is it called the Swan Nebula? And it's just because a lot of astronomers saw it and were like, that does look kind of like a swan. So this star-forming region is in the band of the Milky Way. It actually is an area that sometimes can be visible with the naked eye in very, very dark skies like the ones we have. They almost look like an area of the Milky Way is slightly brighter than the rest, kind of mess with your eyes if it's there or not. But this star-forming region that we have here is an estimate about 6,000 light years away, about 15 to 20 light years across, and contains about 10,000 stars. And all the little stars are being born in there. And as time goes on, you eventually reach a point where no more stars can be born, and that gas gets blown away. And then we get the rest of the stellar evolution process. Yeah, so let's speak of the stellar evolution process. Go back to the binary stars, which are the really cool odd ones out of this. Well, we say odd ones out, but based on current research, and correct me if I'm wrong, Teznie, but like we now think like about half of the stars in the sky might actually be binary systems.
Yeah, so if you go outside and look at the sky, roughly 60% of the stars you see contain more than one star in that system. Okay, so yeah, now I'm going to move on to what happens in this evolutionary process when you throw a second star into the mix. So we start with two stars that are born almost simultaneously. Sometimes they will have similar masses, sometimes they will have quite different masses, but are gravitationally bound and in orbit around one another, but close enough such that when the first star of this intermediate mass, so 1 to 5 times the mass of the Sun, moves into its red giant phase, is large enough that the surface of it is close to the secondary star and mass begins to transfer from one star to the other. And what this causes initially is you start to see an overmass in the secondary star. So what would normally happen, based on the kind of conversation we just had, is that the most massive stars evolve first. So they very, very quickly burn up the hydrogen in their core and move on to fusing other elements. And you can think of that very similar to if you have a very hot, very powerful, very large fire, it's going to use up its fuel much quicker than an embered fire where it's small and the mass of fuel is small. So what we end up seeing are systems like Algol, where they are unintuitively backwards, that you have a red giant that seems to be low mass, but that is an evolved portion with a blue main sequence star that is higher in mass. And what we know is that star has become blue and become heavier because of the mass transfer from the primary component. So that's the first stage of mass transfer. Then what happens is you end up with, you get a bare core white dwarf, just like you would with a single star, but now you've got this overmassive secondary component. So that may have been, a small M dwarf that wasn't really going to do anything exciting, but now it's a much, much heavier star. And then it itself is going to evolve, and then it's going to fill its Roche lobe too, and this is going to transfer mass now back onto the white dwarf. And this is what T Corona is doing. So the T Corona system is a red giant with a white dwarf in orbit around it. So there was a star that evolved at some point in the past and left this bare core white dwarf behind and transferred its mass onto the other star in the system. That star has now evolved and is transferring mass back onto the white dwarf. So as it's doing this, white dwarfs are what we call degenerate objects. So they are at a very specific mass limit where they cannot take any more mass. And that's to do with the physics of the particles that they are made up of. So when you start to add mass onto the white dwarf, it becomes unstable. And periodically, it will burn off in a very short period fusion reaction all of the material that's been dumped onto its surface that is over the mass limit for creating that object, and that we will see as a nova. So that is what we are expecting T Corona to do, and these can be much shorter period systems in T Corona. T Corona is actually in a classification of long period systems, but you can have systems where what this actually leads to is a supernova, which is not a nova. They are different. So a supernova is completely cataclysmic. What you get from the other end is, in this case, you would get a neutron star instead of a white dwarf at the core of that system, and there would be some disruption to the system as a whole. As a binary system, you may be left with a red giant and a neutron star, but it will depend on the dynamics and how close the two systems are together.
So would the star survive that, like the companion star, the supernova?
It depends how close together they are. Some do.
Oh.
Because stars are much bigger than we think about and we can really imagine in our heads. So the distances are extremely large. And these are all classes of what we call cataclysmic variables. There are many classifications of cataclysmic variables, but they are typically involve different types of novae or type 1a supernovae. And they always involve a white dwarf binary system, a white dwarf with another star in an evolved state. And what makes them different are the orbital periods and the distances between them, and the formation history of the system.
Okay. And actually, on the subject of novae, I do have what's something that's left behind from some of these, which is a supernova remnant. So here we have one known as the Eastern Veil Nebula, or actually it's just part of the Veil Nebula. This is a supernova remnant, as you can see, kind of looks almost like those smoky tendrils in the view, is part of this remnant. And this thing is huge. So basically, if you could see this, if this was as bright as a full moon, to put into perspective, it'll be about 6 full moons in diameter across the night sky. I can't even try to get this whole thing in view of the telescope. I'm actually surprised I got as much as I did in view. Because these kind of like cool tendrils, we think the star that created this might have died about 10,000 to 20,000 years ago, and it's about 2,400 light years away, just kind of going kind of near the constellation of Cygnus in the sky. This can be seen through other telescopes, but it's a something you might need a filter to actually help you determine this. And for those of you just showing, this is what the telescope's actually seeing. A bit of a longer exposure. Right now, there's a minute exposure going on with this image, but you can still see all those cool details. You can see why it's called the Veil Nebula. It kind of looks almost like a veil. Some other have said it looks kind of like a river. I've also heard some people say it looks almost like spider webs, almost like a spiral web that's been disrupted. Just a really cool formation. And speaking of cool formations or things that might do cool formations, now might be time to get to this star of the show, TCRB itself.
Thanks, Saul. So this is a great, I think you've probably all seen this. It was on the banner ad for this live stream. It's been in many news articles this week. So this is an artist's impression from Goddard Space Flight Center of what the T Corona system might look like up close. So to highlight kind of things we already spoke about, what you're seeing in this image is a red giant star. And in the center of the weird white gaseous disk is our white dwarf. And you're seeing mass being transferred from the red giant to that white dwarf. And in this rendition of it, you're also seeing the artist's impression of the nova explosion as the mass limit is exceeded and the white dwarf burns off its material. So I'm going to go into what's the story so far and why do we think T Corona Borealis is about to have a nova event? So I asked Saul to pull up the history, but I'll go into the history as an astronomer, right? So there was a nova event in the 40s where this traditionally 10th magnitude star, so something you can't see by eye, was suddenly visible with the naked eye. And what data from that time told us is that for about a year before it became bright enough to see from just standing outside by eye, there was a pre-eruption dip in the measured magnitude, so the measured amount of light that we can see from this star. And you'll see that in the upper left plot there. So approximately a year ago, so early in 2023, this dip started to be seen again. So the data on the bottom left, both of these plots are taken from the AAVSO. And the lower one, the lower right image, shows what started to happen in 2023. So we see the bottom line is the measured amount of light we're seeing in the blue, and the top line is the amount of light we're seeing in the visible. And both started to dip early in 2023 and have maintained this lower flux level since then. So based on this dip and the measurements of it since then, there were forecasts that we should expect the T Corona Nova anytime between January and September of 2024. And we haven't seen it yet. So we're still waiting. And current forecasts say maybe January, but it could, again, be any time between now and January. And as Saul and I were talking before the stream started, right, it could be this evening, and that would be amazing. What I was also saying to Saul is, as a scientist, if it doesn't go nova and it goes back to just stably sitting at 10th magnitude, that's really interesting science. I think the most interesting science always happens when something happens that we don't forecast, right? So just like when we looked out into the universe expecting to see other stars, other planetary systems that looked like our own, and they didn't, that makes us need to remodel our expectations. So if this doesn't go nova, we have to go away and think about what that means, and that's really exciting. But if it does, that's also exciting because that means our forecasts were right. But we've seen a much longer time in the dip this time around compared to the 40s. So that is also telling us something about the physics of the system and things that may have changed. So we will have to spend a lot of time studying why that has happened to understand, is the physics of the system changing, and is that predicting something for the future?
Yeah, gives so many questions. Yeah, and I do have TCRB in view. We'll say, as we said, it's a very dim star. So, for example, when I was showing Alberio, that exposure time was like about like half, like a less than a second. This is currently exposure of 15 seconds. Little bitty. So there's not really much to look at right now. But if things go well on, it's like it may not be cool science, but I kind of want to see something cool visually in my lifetime. Like if this does go off, it will become a lot brighter than this.
And I'll say it's already cool science. As I said, we've already been well beyond the 1 year mark of it being dimmer. So there's already some cool science in that. Something we're doing as astronomers is looking at the spectra of this star. So these type of stars have really interesting spectral features, as you can imagine, right? So they are dominated by the spectrum of the giant star because it's emitting more light at this point than the white dwarf component. And that's because it's much bigger. It's still fusing at some level, even though it's not fusing hydrogen in its core anymore. It will be shell burning other elements. So it's still generating new energy. Whereas the white dwarf is just a thermal component now. It stopped fusing long ago, and the light we see from it is just the thermal energy as it is cooling. And eventually we won't be able to see the white dwarf component, right? You know that it will cool to the point that we can no longer observe it. But what we see in these systems typically when they're quiescent and not doing anything is the spectrum of the M giant with these really sharp emission features from the white dwarf and from the white dwarf exciting the material from the M giant. And then when they go nova, the spectra completely changes. We suddenly get these really broad emission features because the material is moving so quickly because of the explosion from the surface. So we see spectral
Ooh.
that are 4,000 kilometers per second wide because of how fast the material is moving. So it's going to do a bunch of interesting things that's great to study. So there's been a lot of pre-eruption spectra being collected. There will be a lot of during eruption spectra collected, like telescopes around the world will turn on this as soon as it brightens to collect that data. And there will be a lot of post-eruption spectra collected so we can really understand the physics behind what we're seeing in the sky by eye.
Ooh, that'll be so cool. Yeah, like even if it doesn't go off, like as I mentioned before the stream, I have a degree in astronomy, and I didn't even really know what novae were. Like there was a difference between both. I just saw it's like, oh, it's an abbreviation of supernova. And it's like now even with this, I've learned more, and it's like, oh, I didn't even know I was excited about this event, and it didn't know about a year ago, and now I have been reading up and learning more just about it in general. So just the science is cool, like with algal and this and like different types. It's really cool.
And this is a system we are actively collecting data on this system as it is in pre-eruption. And we'll continue collecting data on it as it works through its eruption and post-eruption phases.
Ooh, it's gonna be nice. Well, kind of speaking of the eruption and post-eruption phases, I think we should dive back in how it's gonna look like when it reaches that point.
Yeah, so eventually the red giant star in the system will itself stop fusing any elements, right? So it will itself become a white dwarf if the secondary component hasn't been through its supernova phase before that. The system's quite wide, so we may not expect it to do that. I'm not going to speak with any authority on that. It's not my field, but let's assume it continues to evolve as it is right now, and we see these periodic recurring novae. Eventually, that red giant will continue through its evolution and it will shed its shells and leave a white dwarf behind. And this will result probably in a planetary nebula. And when I was an undergraduate student, we were taught planetary nebulae were caused by the shells of gaseous material slowly ebbing off of these giant stars, leaving behind a core white dwarf. And this is actually a really hotly debated topic in the field of stellar evolution right now is, do you actually require binarity to cause planetary nebulae? many of the planetary nebulae that we look at, like this one, which is, I've got wrote it down, give me a second, the Southern Ring Nebula, is this was a known binary system. This is the image taken from Hubble. And you can actually see both stars there in the image from Hubble. And at this point, it was already a white dwarf and red giant. So there was already a planetary nebulae forming around it from the initial white dwarf evolution. But what they have found with James Webb is this is actually a 4-star system, and 4 stars have interacted to cause what we're seeing in the planetary nebulae. And there is growing evidence that you require interactions from other stars to cause planetary nebulae as we see them. Again, that isn't my field of expertise. I've heard it from people I speak to, but it's an ongoing discussion in the field. Some people know you can get planetary nebulae around single stars. We're just seeing the distribution effect that 60% of all stars happen to be binary or multiple. And that is impacting what we're seeing in their evolved components and dead components as well. So that is an ongoing debate that's going to require a lot of research. But we will expect that T Corona at the end of its life, when the red giant has lived its time and stopped fusing elements, that it will result in a planetary nebulae of some kind in the Corona system, in the Corona part of the sky.
Ooh, that'd be really cool. I wonder if they've done like animations or like animation might not be the right word, but more like simulations of how that might look like given the system.
I don't know if they have for this star. There are a lot of how do planetary nebulae form models and simulations out there, because forecasting how we get the various different shapes of planetary nebulae is quite difficult. Right, that you can put a lot of pieces in, and generating the variety of different shapes that we see in the sky is actually really difficult.
Ooh. Yeah, well, speaking of some of those shapes, I have an example of one here, one of a target that actually is visible through a telescope and was actually the first planetary nebula ever discovered. Meze 27, also known as the Dumbbell Nebula. So some see like the dumbbell shape, kind of like you can tell like it's a bit thinner in the middle. As you go through the edges, it gets thicker, almost like weights on the sides. The one I personally find easier to find, the other name it's known as, is the Apple Core Nebula. Because it kind of looks like an apple core, like a giant space apple that's been eaten. Do not want to run into the thing that ate that apple, because this thing is like 3 light years in diameter, which would put it about 18 trillion miles across. So that's how long the drives from here to Austin feel like sometimes. And also, we think the star that created this died about 15,000 years ago. It's about 1,360 light years away from us, and we think this nebula is kind of a bit of like almost like a football shape, like American football shape, and we're just seeing it from a different angle. Some other ones, kind of like the ring nebulae, have also look like these, but they can also give you some also really cool effects. So this was an image I took on this telescope a few nights ago. Just sadly, this object is not high enough for the stream, but it is a really cool one. And Teznie, I know you said it's one that you personally very like a lot as well, which is the Helix Nebula.
Yeah, it's my favorite. And these are both examples of central double stars, right? So they don't look like double stars when we look at them, but the astrophysical measurements tell us that there is a binary star at the center of those systems.
Oh yeah, and I always love like the different colors we get. Well, not the colors, the shapes we get there yet. Because yeah, that's look just like Helix. And actually, now I'm seeing this image like on the big screen because I have a bigger monitor. I think there's a galaxy in the background. Just right there. I see a little disc shape. Guess we got a 2-for-1 special here. And yeah, there's so many cool ones. And again, this is the first planetary discovered. Messier 27 is the other name it's known as. Oh, a question came in from Rosso Doracio. Apologies if I'm mispronouncing the name. Are the nebulae all gas, or are they made of gas and dust or cosmic material? Teznie.
Yeah, so Great question. Initially, they are all gas, right? So it's the gas that was the star or stars. But as it moves away from the star, it can become dust as it gets beyond at certain heating distances. We call it the condensation radius, at which point you'll start forming dust. The reason we see a lot of the bright is actually the central star still radiating. It's heat out, so therefore it's exciting the gases. So when you see dark strings through the nebulae, when you see them in color, that's because you're forming dust. So you're seeing some shadowing. And the bright material is the gas that's being excited by the radiation from either the central star or other nearby stars.
Awesome, thank you. Let's see. I think we've reached the Q&A section of the program, unless there's something else that you wanted to talk about, Teznie.
No, I think the only thing I will say is watch the skies and don't hold your breath because it could wait all the way till January and nobody needs that. But it'll be really great, right? I think we've seen several comets. They generate a lot of interest in astronomy, but this is something completely different. And having the star pattern that we see in the sky change in a natural way with a natural phenomenon that we can explain is really exciting. And I hope you're all as excited about it as we are as astronomers. And as a perpetual astronomer and parent, I hope it really excites the next generation of people that go out in their backyard and be like, oh my goodness, there's a new star. And then they want to become astronomers and do things like this in the future.
Yeah, no, I completely agree. Just get more people into science, into astronomy. And actually, funny you mentioned like how it's changing. So actually, when I was doing some research before this, Algo was nicknamed the demon star of Perseus, because of that change in brightness of variables, some associated to be part of like the Gorgon's head. So they're like, oh, it's the evil eye, just kind of like
Yeah.
blinking at us, and we might get another giant space eye blinking at us. So much, much, much more slowly. Yeah. Well, let's see. And for those of you just joining in, we're kind of in the Q&A section. If you have any questions, feel free to drop them into the chat, and we will answer them. Like one that just came in from Marcus Mitchell: which star is about to explode? Tuned in late. So the right now we're talking, the one we're mentioning is TCRB. That star is really going to go supernova explosion. It's mostly just going to get really, really bright, but it's not going to be destroyed in the process. And maybe Teznie, you might have a better way of summing that up.
Yeah, so it is an explosion, but it shouldn't result in the destruction of the star. So it's not a supernova. A supernova is a cataclysmic event that results in the destruction of the body from which it originated, sometimes leaving behind a neutron star and sometimes leaving behind a black hole. This is a nova, and what's happening is material from one star is infalling onto a white dwarf. And white dwarfs are compact objects that are at the physical limit of how much mass you can fit into a certain volume. So when you add more mass to it, which is what's happening, there's a certain amount of mass it can take before that material will burn off very, very quickly because the object itself can't take any more mass. So it will cause really quick, small nuclear fusion explosion that burns off all of that additional material, and that will see the star brighten from 10th magnitude, which we can't see by eye. Most people can see down to about 7th magnitude by eye. So the brightest stars in the sky are 1st magnitude, the dimmest are 7th. We can see 10th is beyond our vision, but this star will become similar brightness to Polaris, so 3rd-ish magnitude when it goes through that. And it's an almost instantaneous process, but from our perspective. So it will go from a 10th magnitude star to a 3rd magnitude star, stay 3rd magnitude for a little while, and then dim again.
Yeah. So something that came in is kind of like where this is actually located. So the window I just pulled up here is the software you use to point the telescope. Helps out a lot. I don't have to do many. I can just type in where I want it to go. So for example, I type TCRB as point to there. So currently it is kind of in the western part of the sky. And kind of one of the big things that you can notice about it is that it will look almost kind of like this kind of partial ring shape, almost like a C shape. That is a constellation Corona Borealis, and TCRB is a very faint star next to it. So if it suddenly seems like, hey, there's a brand new star just appeared right next to this kind of cool little C-shaped constellation, that is TCRB going nova. Ooh, a question from Joe. Will TCRB be visible in the daytime?
No. So at third magnitude, the sky will be brighter than it as a star, but it will be very visible at nighttime.
Yeah, it would be cool. The one that might become visible during the daytime in the far future, or hopefully closer future, is the star Betelgeuse in Orion. It's going to blow up literally any second or the next 100,000 years. We got a good range going on. And when that one does go supernova, we do think it would be bright enough to be visible during the daytime. So I kind of hope it happens during the winter so we can see it at night, but if not, I will be fine seeing it in the daytime. I just hope that happens sooner rather than later. Let's see. Another question from Marcus Mitchell. So if our sun will do as well, right? It was kind of when you're talking about it going into a nova, about TCRB's process.
Yeah, so our sun won't. Jupiter, unfortunately, isn't massive enough to act as a mass transferring body and then develop some kind of stellar fusion from it. So here's the chart I showed at the beginning. So this is Chandra X-ray Observatory's artistic schematic on stellar evolution. So the sun is the third line from the bottom. There, so we'll have the sun-like star. Once it stops fusing hydrogen in its core, will begin fusing helium in a shell outside of the core. And when it does that, to maintain energy balance, it will start to expand on its outer surface, and it will become a red giant. Sorry, not massive enough to become a supergiant, a red giant. And the inner planets will be cannibalized at that point. Some of them will move out a little bit to maintain angular momentum in the system, but some of them will be cannibalized. And then as the helium shell also stops fusing, there will be, it's not massive enough to fuse heavier elements than that. So then the core of the star is dead. It's no longer fusing anything. So there is there's nothing really left to hold the star together anymore. And the outer shells will begin to move out from the center of the sun, move out through our solar system, through the outer layers of edges of the solar system, and then out beyond that. And you'll be left with a white dwarf star where the sun was. And if the traditional teaching of planetary nebula formation is correct, a planetary nebula in what was our solar system.
Yeah, just like this. All right, let's see if any other questions are coming in. If you have a question, now is the time to ask. We get paid by the question, so the more the merrier. Let's see. I'm not really seeing any more questions right now. So I think that's about it for our program tonight. I really hope y'all enjoyed. Let's see. One that came in from Instagram from RiverJohn14 about how many recurrent novae do we know of and are we tracking them?
Yeah, so we're tracking as many as we can. Obviously, that's what astronomers do. So when we're interested in something, we look for it and we look for more of them. There are a few. I need to pull up the list I was looking at earlier today, because that isn't something I know off the top of my head. But there are several really famous ones. T Corona Borealis is one of them. The other is RS Ophiuchi and T-Pix. So there's three really famous ones that do become, I think they're the three that become visual, so we can see them. But there's a whole slew of others that never become bright enough that we can see them, but that astronomers are studying. So we'll be studying the spectra of them. And the photometry of them, even though they don't become bright enough for you all to see at home.
Awesome. Yeah, one I was reading beforehand is like some say like about 50 a year are seeing the Milky Way. Does that number sound right?
I don't know.
Well, the good thing with
Sorry.
it, there are several that are reoccurring at least. This isn't like a just for this.
Yeah. Oh, yeah. As I said, there are 3 that go bright enough for us to see. And given the size of the universe, that tells me there are many, many more that aren't bright enough for us to see.
Yeah. Oh, and another one from Instagram from Millie Hope. I'm sorry if that's been addressed, but how do you know the star is going nova?
Oh, yeah. So can we bring up this slide? So this is how we forecast it last year. So we know this star has gone nova at least twice before. The most well-documented case was in 1946. And during that period, in the year lead up to the nova, to the brightening to visual magnitudes, we saw a dimming in the star's brightness. So typically it sits there just comfortably. It's variable because it's a binary system with an accretion disk. So there is some variability, and that's why you see this wave-like structure in there. But its average brightness started to dim roughly a year before we then saw a peak in its brightness because of the nova event. So early in 2023, this pattern began again. And at that time, an observing circular was sent out to ask people to start observing this star because we were seeing a dimming in magnitude, and therefore forecasting that roughly a year from then, we should expect to start seeing the star going nova. And that hasn't occurred yet, but it has remained at this dipped magnitude. So it hasn't brightened back to 10th. It is still sat down at the lower average magnitude and lower average brightness. So we're still playing the waiting game of seeing when we will start to see it brightening.
Awesome.
We're also seeing the spectral features you expect to see. So I didn't talk about that, but I did talk about how these stars are spectrally interesting. So you see the M giant is the dominant part of the spectra, but you also see these emission lines. You also see an overlighting in the blue because white dwarfs are predominantly blue. As we approach the nova, what we saw in the past was that the emission lines, the emission intensity goes down, and the blue part of the spectrum decreases in brightness compared to the red part of the spectrum. And that's expected to be due to the buildup of material on the white dwarf, absorbing the light from the white dwarf, and therefore we just don't see it as well. And we are also seeing that in the spectrum right now. So we are seeing these emission lines that we typically see from hydrogen and helium, NOx and magnesium starting to decrease. We've seen them decrease, and we're also seeing the blue part of the spectrum decrease.
Speaking of the variability, a question from Barry Allen. Can you explain the variable periods in terms of days to years?
I'll speak to 2 variability periods, I guess. So the nova period is very, very long. That's how we classify recurrent nova, is that they are long period. Your typical nova are much shorter because the stars are much, much closer together. And you'll see, 5 to 6 year periods versus these long, decades-long periods. The variability in there is due to the 2 stars orbiting each other plus the accretion disk. So that's why it's not just a straight sinusoid. There's all this mess in there because of the accretion and because the red stars are highly variable themselves. But even just looking on this plot here, right, like I haven't studied this star in detail, but you can see there's roughly 8 months apart from spike to spike. 7 to 8 months, I would say, just based on the sinusoids that are put in there. Those are fit sinusoids to the overall general period that's below all of the mess from the system that's on top of it.
Hey. Let's see. I believe that's about it for questions for us. Thank y'all to everyone who joined us tonight. If you're just joining the stream or joined late, this stream will remain up on our YouTube channel, McDonald Observatory on YouTube, as well as all the other streams we've done. We've done over 60 of them so far, ranging not only from Novae, but also Stellar Evolution, Control Room Talks, books we recommend, planets. We've done a wide variety, so if you want to check those out, they are up there. They are up there on our YouTube channel as well as this one. And thank you all so much for joining in. And if you liked it, make sure to leave comments, like, subscribe, all that jazz, so we can keep on doing these. And hope y'all enjoyed. Y'all have a good night. Oh, and also, almost forgot to say, you can actually come out and visit us. We do have a visitor center. You can visit the telescopes, just McDonaldobservatory.org, and you can come out and visit. We're open basically year round and do nighttime programs, usually Tuesday, Friday, and Saturdays. Yep. Okay, now goodbye for real. Good night, everyone.